Recording. Yeah, hi, good afternoon, everyone, and thank you so much for joining us again for the continuation of our data structure series. So the last session that we had, it was a wonderfully successful session where Pavithra had given us an introduction of trees. Now she will take it forward in continuation to the previous one, and we will be talking about BST today. So I think Pavitra's introduction we are all aware of. So Pavithra is Director of Women Who Code Chennai, and she is an MTS 3 at VMware. And yeah, so I'll hand it over to Pavithra and looking forward to a wonderful session yet again. Over to you, Pavithra.
Hey, thanks, Shubhanjali. Thank you all. All right, I think I'll quickly start with today's session. Hope my screen is visible to you all. Can someone confirm?
Yes, it is visible.
Yeah, sure. Let me move on to the content for the today. Yeah. So I think as Shubhanjali mentioned, it's going to be trees again. So when we say trees again, we'll just quickly do a recap of what we saw in the last session. So I'll not go too much detail into it. So we have already covered binary trees in the last session. So yes, so this piece of thing is already covered in the last session. So binary tree is nothing but a tree which has only two children. So at most two. It can have 0, 1, or 2 children. So that's what we saw in the last session. And this is a classic example of any tree because it doesn't have any rules followed and it can have multiple children. So it's just a tree. And we already spoke about complete binary tree and perfect binary tree. So we have the recordings uploaded in our Women Who Code YouTube channel. So maybe you can have a quick look at that. So today we'll be covering about binary search tree. And we'll talk a little bit about two flavors of it, which is AVL and Splay trees. So I'll move on to the next slide. So yeah, so this is the agenda that I've thought to go through today. So a bit of what is what and the terminologies and representation, the similar things that we did in the last week's session. All right. So yeah, I think the basic of binary search tree is something which we are little aware. So I'll go through again. So it's a hierarchical structure and it's not a linear one. So when I say linear, it is more related to your linked list or stack or something which is going to be on a line, like an array. Okay, so the structure itself is a non-linear structure. So that's why we call it as a tree. When it comes to binary search tree, the major condition that we just have to remember is the keys. So key is nothing but the value. So the value that is in your left side of the tree, left side of any node. When you consider this as the node, this is your left subtree and this is your right subtree. So any key that is in the left should be lesser than the node, and anything that is on the right should be greater than this. So that's the thumb rule. We just have to remember that. And this is an example. So you see 3, 8, 10. And the key point is the last point. So left and right subtree should recursively be binary search tree, as in it should not be only for this, it should be recursively. Even within, it should follow. So when I say this alone as a tree, it should also follow. So 1 less than 3, and again, 6 is greater than 3. We are good. So 6, 4, 7. If I take this subtree, it's going to be 4, 6, 7, which is following the rule that 4 is less than 6 and 7 is greater than 6. So the entire tree should follow this, the two key things. And that's when you call it as a binary search tree. You can put your questions on the chat or you can unmute and stop me if you have any questions. Yes, I think this is a very quick exercise. I think last time I felt it worked well. So I wanted you all to guess this. With the previous example that we saw, what is the tree and what is binary tree? What is binary search tree? So what kind of tree could this be? So maybe with the rules that we already spoke about.
I think it's a BST.
Yeah, that's right. So it's a BST and you can also feel free to ping on the chat. So it is a BST for the main reason that all your keys on your left is greater than your node and yes, less than your node. And again, all of it that is on your right is going to be greater than your node. So that is a little straightforward. So yes, it's a binary search tree. And again, another exercise to confirm if we are really good on this. So just you can either ping or you can unmute and let me know what kind of tree is this. Any guesses? Yes, that's right, Ashok. So yeah, this is a binary tree, and obviously it's not a binary search tree. Reason being, this first one itself will give you an idea that 7 is anyways, it's greater than 2. So this is violating the rule, but still we can call it a binary tree. Why? Because it is having at most 2 children. So it either has no children, 1 or 2. So in that case, it is solving our binary tree condition. So this is going to tell you that it's a binary tree and not a binary search tree because of all these reasons. All right. This is just a basic for us to recollect on what is what. And again, this is another repetition of our previous one. I'll quickly go through this. So it's a representation of binary tree. So any binary tree, these are the key things. Your key is your value. That is the current node, followed by current nodes left, current nodes right. You just have to remember all these pointers. So data, a pointer to your left and pointer to your right. So that's how we represent. It's just a simple Java class. So where you have a key, your left and right nodes, and key is nothing but the item. Item as in the value. It can be anything. It can be A, B, C, D, or any value or anything it can have, and that's how it is. Okay. Okay, all right. So this is something that will go a little deep today. So which in the last class we didn't cover. So operations on a binary search tree. So these are the key operations that we already know that we can do. So now when we say binary search tree, one thing we have to remember is whenever you do an insert, whenever you search or, okay, search will come again. Whenever you do an insert or whenever you delete, you have to ensure that the thumb rule doesn't break. The rule as in the left and the right greater than lesser. So that should not break. So that's how we are going to do it. Okay. So we'll start with search. So I'll just tell you how do we do it. So consider that this is your tree. And we are going to say that we are going to search for the key 30 here. Okay. So how can I go ahead with it? So it is always recommended that you start with the root. Root node is something that you obviously know. So first thing, 100 and 30. So what do? You compare your 30 and 100. So is 30 less than 100 or greater than 100? So if it is lesser, then what do? You move to left. And if it is greater, you move to your right. Okay, so this is pretty straightforward. So in this case, what I'm going to do, I'm going to move this side. That is my left side. So here, what I do again? So I'll do 30 and 20 comparison. So is 20 and 30, when you compare, is 30 lesser than 20 or greater than 20? It's obviously 30 is greater. So I move to my right side. So coming to the right side, here I have to compare 30 and 30. Obviously, you have found your key. So now it is done. So key found. So this is how we travel through a tree when you have to do a search operation. Okay. So one thing that I can probably give as a disclaimer here is today we'll talk about the concepts alone and how do we implement and which language. It is something that depends on individual's comfort. So we will try to understand the concepts of binary search tree, and in any language, you're going to implement it in the similar fashion. So you keep traveling towards the tree, go to the left, go to the right, compare, again, decide on left or right, and ultimately you'll know if you have found or not. Okay. So now you're going to, this is another example for 200. So 200 is something which is starting from the node. Is 200 greater or lesser? Obviously it is greater. I go to my right. And in this case, what will happen is 200 greater or lesser than 500 is obviously lesser. So I have to go to my left side. And when I try to invoke my left, there is nothing, it's empty. So which means it's not found. So key can be there or cannot be there. So this is an ideal example of any minor problem that you get, like finding a value in a tree. So if somebody asks you, how do you do it? This is the approach that anybody can follow, and you confirm whether key is found or key is not found. Okay, so this is little simple, I believe. You can ping me for any questions. You can put it on the chat or unmute. Okay, I'm assuming you're good. So yeah, this insertion. So insertion is something which we can go a little slow here. So imagine there's an empty tree. So there's nothing in the tree and we start with a fresh tree. So what do? We insert our very first node, that is 100 in this case. And after that, we have to progressively insert based on the same thumb rule. So how did 20 come and sit here? That's because 20 is less than 100. It'll go and sit here. Again, 10, it is again less than 20, it will be here. 30 is greater than 20, it will be here. Okay, this is just a simple thing. So imagine that you already have a tree and you're going to insert 40 here. Okay, so how do we do it? So you have to travel from the beginning, left, decide left or right, and then move to left, again decide left or right, move to right, and finally insert it here on the right of 30. Okay, so I would like to repeat that when I said insertion or search, we just have to ensure that we should not forget the principle. So once you remember this basic principle, it's going to be a little easy for us to find a position for it and insert it directly here. So in this, can someone ping me, where do we insert, say 200? If I have to insert 200, so which would be the right position? You can tell me like left of something, left of this node or right of this node. That's right. Yeah, that's right, Geeta. So it's going to be left of 500. So obviously, right, because that's the only position you have at this point in time, and it's going to sit in left of 500. So that is correct. Yeah, right. So we'll move on. All right. So I have an exercise immediately after this deletion to do all insert, delete, and all. So we'll do it together that time. Now, coming to deletion as a concept, what we can do here is, so three possibilities are there. In a tree, if you have to delete a specific node, you can be under three different circumstances. One, the node to be deleted itself is a leaf node. Leaf node as in the bottommost area, right? So if it is a leaf node, then there is nothing much you have to think about. Just eliminate it quickly, like remove it from the tree, delink it, mainly delink it, and you're good. You're done, and your remaining tree is intact. So the second case is something like if it has one child. So say, suppose this is the example. If it has one child, what are you going to do? And the third case is, we'll say it as a worst case scenario where it has two children. In that case, how are you going to delete it? All right. So first case, delete 9. 9 is what? 9 is your root node, like as a leaf node. So no worries. You just have to delete it, and your tree structure remains the same. It is still following the principle. Nothing has changed. So you can still call it a binary search tree. We are good. Now, when I say delete 7, it's going to fall under this second category. That is, it is having one child. So in this case, imagine if I delete 7, what will happen to 6? Or since I have to delete 7, should I also delete 6? So to handle this, what we have to do is, this is the rule. Copy the child to the node and delete the node. So this is what we have to remember. You have to copy the child to the node and delete the node. Okay. So copy 6 here and you delete it. Okay. So that is solving your problem. If at all you feel like 8 is here, like, it has a right child and there is no left child to it. Again, no worries. You can copy 8 here and delete 7. Either ways, it's going to follow this rule. So just remember, if it has one child, we just have to copy the child, the data, the contents in the child node to the current node and delete this. All right. So now we'll go to this.
I have one question, Pavithra. So, say for example, we'll take the tree on the right, the second one maybe. No, on the top, on the top, on the top,
Okay.
on the top. So if in case if I have to delete 5, so I'll push 7 as the parent and 6 becomes my child. Is that right?
No. This is something which will come in the later slides, Shashu. There is something called rotation, which we'll talk about it. So for now, we're taking baby steps. So we'll go slowly. So 5, when you say, what did you say? You said 7 as a parent. No, it will be 6 as the parent. I mean, 6 as the root node, and 7 will be on its other side. This side. 7 will be intact. 6 will go here. But how is it going there? That will come up in the upcoming slides. Okay. So because we are talking about the leaf node, as in when it is at the bottommost and when it is this way, single child. Okay. So in this case, we cannot call that 5 has only, so 5 has 2 children, but 7 has only 1 child. So the only criteria we are talking about is these 2. Okay. So you can just forget about all those that has 2 children. We'll come to it in the next slide.
Pavithra, I have one more doubt on that.
Yeah. Oh, I'll do that. Sure.
I think you will cover in the next session, maybe. So we are deleting the 7, right? Once the 7 deleted, we move the 6 to under the 5.
Correct.
Yeah, that will how we will capturing the 7, the parent, like that, or
No. See, so these are something like, for now, we'll imagine as a concept. As a concept, what we have to do is, 7 is the node. Okay, so wait, I'll go back maybe a couple of slides and then I'll tell you. Like programmatically, if you have to just imagine how it will be, give me 1 second. Yeah, so here, right, here our node is going to be 7. So 7 has left and right. So in our case, it'll have only 1, right? So with this as your coding base, you just have to imagine this as your structure. With this as a structure, I'll come back to the same slide. And so here, this is your node, this is your left, there is no right. So you're going to copy the contents of your own left child to yourself, to that specific location, which means this pointer will not be disturbed. It is already pointing to this, right? So you're not going to disturb anything. So in your data structure, you play around with memory and your pointers, right? So this pointer will be intact. You're copying the contents of this to this, and you're going to remove this arrow, right? This gets delinked. So you can just leave it like as if it's deleted, and it will be intact. Okay, so that's how it would. Okay.
Good. Thanks.
Okay, yeah, thank you. So this is the last scenario where it is like it has 2 children. So what will happen is, this is something, again, we just have to remember it this way. So whenever you have 2 children and you have to delete the node with 2 children, first is find in-order successor of the node, okay? And copy the contents and, okay, this is a little theory, so I'll leave this part. I'll come to an example, then you'll understand this better. So first, what you have to do is we have to find the in-order traversal. I think last class we spoke about in-order traversal, which is nothing but your left, root, right. So if I say we are going to delete 3 and it has 2 children, what I'm going to do is first find in order 1, 3, 4. Okay, so just put your in-order traversal and in-order successor. When I say successor, the successor of your 3 is the node to be deleted, and your successor is going to be 4. Okay, so now we found something that 4 is our targeted one. So what do we have to do? Copy the contents of this 4 to your node and delete this link. So 4 will come here and you're going to delink this. Okay, so now your tree is intact, everything is intact. Again, there can be one more question. Can I take the predecessor? It is still okay. So you can still take the predecessor, but the preferred option is to take the successor. Reason being, your tree will look a little complete in this case. So 1 is intact. You can also copy 1 here and remove 3. That is still okay, but it won't look like a proper complete tree. So to make it a complete tree, you just have to ensure that you copy the successor of it. Okay, so we'll just remember 3 steps. If this is the node to be deleted, first step is to find the in-order traversal. 1, 3, 4. And in your in-order, take the successor. Take the second, like the one that comes after 3. So you're going to copy the contents here to your current node to be deleted and delink it. Okay. So if we are all good, we'll do a small exercise based on this one. Okay. All right. Okay, we'll start with this. So before going to these 3, I'll ask a quick question. So I have to find 7 in this tree. So what would be the first step that we'll do? So based on what we saw in the previous slides. So how do we start? Where do I start from? So maybe you can answer that first. You can ping it here. If 7 is going to be something that I'm going to search, where do you start from? Right, from 5. That's right. After that, what would be your first comparison? Can someone tell me, like, how do we, from 5, what do we compare? Okay, so I'm not getting it. So 7 is the value to be searched. So what do? We have to compare our key value with the root element, right? So we say is 7, that's right, element, yeah. So we have to say if 7 is lesser than 5 or greater than 5. If it is less, we go to the left subtree. If it is right, we'll move to the right subtree. So in our case, 7 is going to be greater. So we are going to move to the right subtree and we are finding the key. Okay, so just imagine, just remember all these key things alone. We'll move to the first question. So where should I insert 10 here in this tree? Which is the right position for 10? right of 7. That's correct. So how do we go about this? The answer is right. So based on what we read just now, so what kind of steps we would do to achieve this? Where do we start from? We still start from the root node. That's right. We start from 5. We do the same thing again. We'll check the left and right. We'll check if 10 is going to be greater than 5 or lesser than 5. Now 10 is greater than 5. Move to right. And in right, we have 7. Now compare 7 and 10. So it's 10 greater than 7 or less than 7. 10 is greater. You move to the greater, like move to the right and you insert here because its right child is empty. So you can go ahead and insert it here. All right. That's correct. So 5, 7, 10. So this is the order we do, and that's how we have achieved it. So the reason why I'm insisting on like how we go through is these are just conceptual examples, right? So imagine in real time, it could be anything. It could be a little different also, and the tree could be a little bigger also. So when we write it, put it as a code programmatically, we are not going to compare 5 and 7 there. We're going to compare, say, node left of node is greater than my key, or node dot right, or something like that we'll be writing. It's going to be a generic code, so we have to concentrate more on how we do it. Okay. So now coming to this question. So delete 6. So what is the process to delete 6? Before that, we saw 3 scenarios, right? Out of that, which scenario does 6 belong to? Is 6 child, like leaf node? Is it directly we can delete it, or do we have to do something and delete it, or how is it? That's right. Yeah, Mary. So it's a leaf node. So in that case, how do we delete it? Should we do something, or it's straightforward, or like what do we do? Just delete. That's right. So we'll just delete it, and it's going to be it'll just go away from your tree. So your tree structure is still intact, and you're going to delete it directly. Now, that's right. Yeah, Geeta. So it's directly you can delete it. And now delete 5. So how are we going to do delete 5 here? After this, okay, I'll put it this way. Now imagine 6 is done, and after that, you have only 5 and 7 left. So how do we delete 5? Okay. So in that case, what would happen is it will have only one child, and then we'll start deleting it. Okay, we just have to copy the contents of your right subtree, right child to the parent, and you're going to delete 5. Okay, maybe it, copy 6 in the place of 5 and delete it. That's correct. That's how it would be. When you delete 7, you have to copy this, and you're going to delete it. The tree might look a little awkward. Tree might not be having anything on the right, but anyways, the approach is correct. That's how we do. So now I'm going to do something this way. Okay. So now imagine we have inserted 10. I think whatever you guys said is right. You're going to insert 10 here. And here we are going to delete 6. 6 is a child node. We are good. In this scenario, can you tell me how are we going to delete, say, 7 or something? Anybody want to give it a try? Delete 7. It's something which is similar to what Geeta had told. In this tree, how do we delete 7? What do we copy where, and how do we delete it? That's right. Copy 10 to 7 and we are good. So far good. And now, if I have to tell you that you have to delete, okay, you have to delete 5, what do we do? So probably, I think Ashok, this would be your initial question. So based on scenario 2, what we spoke, if you have to delete 5, what would be the step that we have to take? Okay, we'll do it together in that case. So what would be the in order traversal of 5? Can someone give it a try? I can still help you. So in order is going to be your left, root, right. So what's going to be the in order traversal of this tree with respect to 5, how do we travel? 1, 3, 4. And then it's going to be your left, your root, and your right. Okay, all right. I think maybe I'll show this. It's okay. All right. So this is your in order. So how do we do in order traversal? Your left, root, and right. Within this, again, left, root, and right. So it's going to be 1, 3, 4. That's your left, entire left. Within the left, it's again in order, followed by your 5. Okay. And then your right side. In your right side, if I have to do a in order, there's nothing this side. So I'll directly go with 7 and 10. Okay, any questions in order traversal? Maybe if at all, I'll progress. All right. So this is your in order traversal. So what were the steps that we saw? First, find the in order successor. To find the in order successor, you write your in order traversal. You have to travel through the tree, write down your in order traversal, and in that you're going to find the successor. Successor is nothing but your 7. Okay, and 7 is something that you're going to copy here, and you're going to leave it this way. Okay, in this scenario. So we might have hundreds of scenarios in mind, but the core thing is the core logic remains the same. You just have to calculate it based on the scenario, and you just have to get your in order, take the successor, delete it, move it. Okay. Any questions around this? Okay, all right. I'll probably proceed.
I have one question, Pavithra. So go to the left. So this is unlike the tree is unlike what we had in the previous illustration, right? So as in, like, you don't have a left node under 10. So if in case if I'm going to say if we take the first tree, if we don't have a left node under 7. So if I have to delete 5, say if in that case, if I have maybe 6, then again we'll go through in order successor of the node. Is it as in, like, we'll do that left, center, and right? Is that how we traverse?
Correct. It will be that way. But in certain cases, what would happen is this is a binary search tree, right? It doesn't have any rule on balancing it. So there is a concept called balancing, which I'm covering in the next slide. So when it comes to balancing is when we have to worry about pushing all of it to one side or pulling all of it to the other side. In this case, if I remove 10, this is going to be empty. Your right subtree is going to be empty, right? We don't have to worry about it. In your case, your question is something like you have a child here, and in this case, if you delete it, what would happen? So we have to follow something called rotation, which is again based on a flavor of BST. It's not actual BST, it's a flavor of BST where you have additional conditions, and based on that rotation condition, something that I told you in the previous time also, that you copy your the bottommost node as your parent, and you leave this link as is, and you delete 5. Okay. So this one, whatever we are talking so far, is about a normal binary search tree, which doesn't even have any specific condition. It just has the basic thumb rule that all your left and right should be, the lesser and greater criteria. So other than that, we don't have to worry about anything else. So based on your, based on the values that is there, you can either take your successor or your predecessor and go ahead, copy, delete. This could even be a recursive process. So all of it that we are talking here is a very small tree that I'm talking about. Imagine the basic application of it is like a dictionary or a spell checker, which we use, right? So there they used to implement binary search tree, which is going to be enormous. So in that time, any operation that you do will be recursive. So you have to do it at every level of your tree and you have to achieve it. Okay.
Sure, thanks.
Okay, so we'll go to something called self-balancing binary search tree. So this is these two are the flavors of it, but for that, we just have to understand what is balancing, like self-balancing and all. So here they concentrate more on height of a tree. So these two trees, it has a nature that it always concentrates something on the height, or rather I can say each of it has its own variant of a binary search tree. Okay, so just to ensure that they keep their height as small as possible. meaning the scenario that occurred here. So when I remove 10, what will happen? The height of left subtree is going to be 2 and your right is going to be 0. So this is something that is not agreed when it comes to such trees, mainly AVL trees. So that is what is called self-balancing trees. When I say self-balancing, it is something like here we never had any information of adding 10 here. And if at all I have to add 11, I'll not even worry about it. What I'll do, I'll go ahead, add 11 here. Again, if I have to add 12, I'll keep on adding it as its right child. So nobody's going to ask me because it's a normal straightforward binary search tree. We are still following the thumb rule. Once we talk about this self-balancing trees, that may not work. It may not work that way. So we'll go to what is AVL tree. So AVL trees are something where this is the rule for AVL tree. Your height of your left subtree and the right subtree should be at most 1. It cannot be more than 1. So looking at it, you can say, right, so this is a little longer, like you have 1, 2, 3, 3 edges here. Here you have at most 2 edges. So which is 3 minus 2 is 1. This is okay. This can be called as an AVL tree. Whereas the moment I delete 17, it's going to be 3 this side and 1 this side. So 3 minus 1 will be 2, which is not allowed, and you cannot call it a AVL tree. So when I say AVL tree, one thing that we have to remember is the balance factor, where it is requiring us to maintain the balance factor at any cost. At any cost, as in, even if I insert something, we have to be mindful of not disturbing the balancing factor. Okay. So that is all about, that's a key point about AVL tree. Just give it a try. We'll see just for our understanding. I have 2 trees here. I'll tell you, one is a binary tree, one is a AVL tree. So probably you can let me know what is the first one? You can probably type it here. So what kind of tree is the first tree? So we'll start calculating the height. So height from here is 1, 2, 3. That is my height of my left subtree. Your right subtree is going to be 1 and 2. Okay. So 3 is the height of left subtree. 2 is the height of right subtree. So what kind of tree is this could be? 3 minus 2 is 1. Can someone want to take it? Okay. Yeah, it is a binary search tree. Like all of it is a binary search tree. One is just a binary search tree. Other one is an AVL tree. So which one could be AVL tree and probably why? Correct. That's right. This is an AVL tree. I'll probably go back to this slide. Maybe I'm not sure if I rushed it a bit. So the thumb rule of AVL tree is it is still a binary search tree. The only rule that you have to check is the height of left and height of right. You have to subtract them. And if it is going to be 1 or it is equal, it's okay. 1 or 0, it's okay. It should not be more than 1. So that is the rule. So now when I come back here, the height of this is 3, height of this is 2. So 3 minus 2 is 1. So this is a AVL tree. How about this tree? The second tree. Can I call this an AVL tree? No, that's right. So what do we do to assume? Correct, the difference is 2. So 1, 2, 3, and this is 1. So obviously 3 minus 2 is, 3 minus 1 is 2, and this is not a AVL tree. So this is just for us to remember. So when we have to think about AVL tree, one thing that should come to our mind is balancing factor. AVL tree is a self-balancing one, and it will always ensure that this one extra is okay, but you cannot do too much of this sort. Okay. So the height difference of 1 is okay, not more than 1. Okay. So now we have discussed about how an AVL tree would be. So how can it maintain this height balancing and all? We keep inserting, we keep deleting, we do a lot of operations. So in order to maintain this height balancing factor, there is something called rotations that an AVL tree will generally do. And it has two things. So one is single rotation, other is double rotation. We'll go one by one and we'll go a little slow. So single rotation is something like you just have to rotate just once, either left or right, to balance the height. Okay. So now imagine this is the tree. Imagine 7, 3. 1 is a new value that I'm adding here. If the tree is going to be only 7 and 3, we are good, no worries, because your left height is 1, right height is 0, 1 minus 0 is still 1, it is an AVL tree. The moment I add 1, what would happen to the height of it? Can someone tell me what is the height of this tree? This 7, 3, 1? Height of this tree, 7, 3, 1. Correct. So height of the tree is 2. In this case, height of right subtree is going to be 0. So 2 minus 0, it is 2, and it is not an AVL tree. We cannot call it AVL tree. So what do? We have to do a single rotation. So in our case, it's going to be rotating this side. Okay, so that is something like right side. You say single right rotation. So the moment you rotate, what do? You pull your root to the right and you rotate it. Okay. And in this case, when I have something like this, you do a left rotation. So you pull it this side and 1, 3, 7. So either ways, it's the same. But we just have to remember that when you keep adding a new value, new key, new node, you just have to ensure that AVL property should still hold good. So in order to do that, we just have to do this rotation and then it will be all set. So now your root is changing. So 7 is no more the root, 3 is your root. And again here, 1 is no more the root, 3 is the root. Okay, so this is simple, like very basic level rotation that I'm talking about here. So any questions here on rotation? All right. So we will just think it at a very high level that we just have to do a rotation. If at all, the balancing factor is not working. Okay. So this is an example here. So 1, 2, 3. So till this we are good. The moment I insert 4, what will happen? Can someone say if this first tree is an AVL tree or not an AVL tree? The first one. Yes, that's right. So this is an AVL tree. So we don't have to worry too much about it. We are good. Okay. Now I'm proceeding further. I'm going to insert 5 to the same tree. So now what would happen? Will it still be an AVL or it will not be an AVL tree? No. That's correct. Like it's quite evident, right? What do? We take 1, 2, 3, 3 minus 1, 2. It is violating the property. It is not an AVL tree. So we are good. Now, in order to make it an AVL tree, what should we do? We should do something called rotation. So that's what we just saw. How do we rotate? We do a single rotation here. Okay, in this case, we do a single rotation. And a single rotation is going to be something that's going to happen only to this subtree. 3, 4, 5. You rotate it and you make 4 as the parent and 3 and 5 would come here. Now it will be an AVL tree. Okay, so this is the pattern that we are going to follow for rotations. So this is a very basic single rotation, left or right, either ways, based on your value that you add, it will keep on changing. Imagine I'm adding 0, -1, -2, my left subtree will grow. Obviously, I'll tend to do a right rotation. In this case, it's going to grow on the right side. So I'm doing a left rotation. All right. So this is the concept of rotation when it comes to AVL tree single rotation. Now I'll move to double rotation, but before that, I wanted to do one thing. So probably I might need your help as well. Okay, I'm going to do something here. I'll just try it may not be little legible, but let's give it a try. All right, just so I'm going to write 2 here. So I'm going to write insert 3. So where do I insert? Probably you can just quickly type on the chat. Should I insert it on the left or right? So 3 is the value that I'm going to insert, right? That's right. Okay, so I'm going to put 3 here. All good. Now, is this an AVL tree or not an AVL tree? This tree. Yes, it's an AVL tree. Correct. So far good. I'm going to insert 4. Where do I insert? Right. Right of which node? 3. Okay, I'm inserting 4 here. So now is this an AVL tree or not an AVL tree? Not an AVL tree. Agreed? All right. So now what do I do? What do I do to make it AVL tree? Rotations, correct. So now which type of rotation should I do? Right, single, correct? Right, left. This side or this side? Left, that's right. So now if I do a left, which is going to be my parent? I mean, my root node, 3. All right. So 3, 2, and 4. Okay. So now is this an AVL tree? The new one is an AVL tree? No, the new one. This one, is it an AVL tree or not an AVL tree? Yes, this is an AVL tree. We are good. Now I'm progressing with one more number, 5. So I'm inserting 5 here. Is this an AVL tree now? Yes. All right, correct. I'm progressing with one more number, which is 1. Where do I insert 1? Left of 2. That's correct. Yes. Now, is this an AVL tree or not an AVL tree? Yes, it's still an AVL tree. It might look like a very bad tree. Reason being, it doesn't have the children filled properly, but it is still holding the property of AVL tree. So we are good. So now if I insert 6, what would happen? I'm inserting 6 here. Correct. That's right. So it is still holding the property. It's still an AVL tree. Now proceeding to 7, what will happen? Not an AVL tree. What do? We do rotation. We do rotation with respect to this. Correct. So single rotation. So I think I just did this exercise to make sure that we are all on the same page. So this is something that you can keep on progressing. But there will be a point where we might not be able to do single or single rotation. So say, for example, I'm going to insert, say, okay, I'll have another tree where 10 is my parent. And I'm going to insert, say 17. I'll insert 17 here. Okay. I'm going to insert 15. Where do I insert 15 here? No, 15. 15 is greater than 10, less than 10. Do we go to the right subtree, left subtree? Yeah. Correct. So this is where we insert, right? So 15. So now I'm going to insert 14. I'll insert here 14. So there will be a situation where we might have to rethink about single rotation. And again, if I have to make it 18, I can keep on doing it, right? So there will be some point where your single rotation will fail. And we just have to go and progress with one more thing called double rotation. So this kind of exercise is something that I'll encourage you to do. Like when you're free, you can probably go through, go through Google or something. Start adding notes and see how it works and how rotation works and all. Okay. So with that in mind, I'm progressing to the next topic, which is double rotation. So there are situations where our single rotation will not always help us. And we have to proceed to something called double rotation. And in double rotation, the usual, the most used is like left, right, right, left. They call it that way. So these two could be very vague to see, but just remember these things. When you have something of this sort, okay, when you have to do a double rotation, right, left, double rotation. When I say right, left, it corresponds to right, left. Okay. So meaning the moment you are inserting something here and one of your tree becomes heavy and balancing factor is messing up, how do we approach it? So what do? This node, your K2 node becomes your parent. And your K1 goes to your left and K3 is intact. Okay, just remember this alone. In your right left rotation, the last node becomes your parent and you push your K1 this side and your K3 will come up this side. So this is kind of a thumb rule that we have to follow in case of right left double rotation. Okay, left right double rotation is something this way, your left and your right. So left, right. In this case, also your K2 becomes your parent. That is like no change in it. But you're going to push your K3 to your right. And K1 will be intact. Obviously, right? Left and right has its own precedence. So here K3 will go down, K1 will be there, K2 goes to the parent. In this case, K3 will be intact, K1 will just come this side. So maybe let's not process too much, just we'll try to understand it. I'll show an example that might be a little clear on this side. All right. I just have one example for it, which is right left double rotation. Okay. So imagine this is my tree. Okay. So we'll go one by one. I'm adding 7. So far till 7 we are good. I'm adding 16. Just forget about 15. Till I add 16, are we good with the tree or not? Is it still an AVL tree or not? I'm asking till 16. Just imagine the tree till 16. Is it an AVL? Yes or no? Yes, it's still an AVL tree. The moment I add 15, obviously what would happen? It'll violate the AVL balancing factor, right? Correct. And in this case, your 15 cannot be on your right. 15 is less than 16. You will push it to your left. Okay. So in this case, your single rotation cannot help you. Single rotation is something that we spoke about, more of left and right of right. So in this case, double rotation comes into picture. So K1, K3, K2, and you can use this as reference. So what did we do? We have to move this 15 as the parent and push this 7 as the, push it down as the child, and this will remain as is. So 15, 7, 16. So now the balancing factor is intact, binary search tree properties are intact. So we are good about it. Okay. So this is how we solve right-left double rotation. Okay. So we might think of how does it really happen in reality. Even I had a similar kind of thought process, but in reality, all these are something that's going to happen in piece of code. In just a couple of 2-3 lines of code, it's going to happen. But our intention here is to understand how the internal data structure works, right? So this is how they keep on balancing itself, and how many ever data you add, like say, the classic example is dictionary, right? In dictionary, you have numerous data like A, B, C, D, you have till Z and a lot of words and many things are there. So it still keeps balancing if at all they use AVL trees. Okay. So you just have to think about the concept of AVL tree. So because that's how I see it. So in the concept, we have something called rotation and it keeps rotating, and we have to ensure that the balancing factor is not messed up. All right. Okay, so this is something that I said, right? Like when you're free, you can try to do it like as a DIY, like do it yourself. Start with one, the way I did, right? 1, add 2, add 3, and it'll fail, rotate it, again 4, 5, rotate it. So it's just an exercise for us to ensure that are we good with the rotation concept or not? Okay. So I think we might run short of time, but quickly I wanted to cover Splay trees. So now coming to Splay Tree, it is again a variant of BST, variant of binary search tree. AVL tree is more about balancing itself and ensuring that the balancing factor is intact. Splay Tree is little different. So what Splay Tree does is it is going to adjust its structure every time you do some operation. Say I do an insert, it'll do some adjustment to the tree. Again, I do a delete, it keeps adjusting. So mainly for insertion or search, when you keep searching something repeatedly, right? This Splay Tree keeps adjusting itself. So the idea is that whichever key that you're going to access, you're going to try touching, that will become your root node. Okay, so these things are little theory. We'll just read through and then we'll have an example. So main thing you have to remember is that it adjusts the structure based on the operations that happens. Operations will be what? Search, insert, all these other operations. And the idea is to bring the most recently accessed or inserted element to the root. So whenever I try to search something or insert something, that will become my root. How can it be the root? Through some lot of rotations, and that is what we call splaying. So this process of rotating, sequence of rotations that we do is called splaying, and that's why these trees are called Splay trees. Okay, so I'll go to the example, and yeah, advantages is obvious. So when I say that something that you're repeatedly searching and I'm going to make it your root, what does it mean? It means that in caching or something, right? The frequently accessed ones will always be easily accessible. Maybe I can imagine it this way. We say that even, something that you search on your Amazon and you go to some other, any normal website to read a blog, whatever, product that you have searched in Amazon will come there in the other website. How does it happen? We say that our browser caches it, right? Caching is something which stores your recent activity in the system and pulls it out every time that you need. So this is mainly this kind of Splay trees, they generally use it to reduce the overall access time, because it obviously knows which are the ones that are frequently accessed, and it always maintains it as the root node. Okay. So yeah, a disadvantage is something like it is not that good as AVL tree. AVL tree had a balancing factor. In Splay tree, it can even grow like abnormally. Abnormally in the sense, it'll have a root and the left alone will grow to a height of 10. There will be no right subtree. So it doesn't care about all those. Its only intention is to ensure that the recently accessed whatever the key is at the root. Okay. So to ensure this, the way AVL had something called rotation, like single, double, Splay Tree is going to do rotations, but the naming is little different and the way it does is little different. So here they call it zigzag. So zig rotation is your single one side, like left or right, and zag is the other side, single rotation. These, all the four are double rotations, combination of your zig and zag. So zigzag, zag, zigzag, and zag. So these many kinds of rotations are there in Splay trees. Okay, so I think we might not have time to cover, but I'll quickly try to finish it off. So zig rotation is something called as right rotation. Okay, so imagine this is a tree. I say splay of 4. Splay of 4 is just like that, but say I'm trying to access 4. So what will system do if I implemented it in Splay tree? I am assuming that 4 is the key, which I always come and, I frequently use 4. So the intent is to make 4 as the root node. So that's what is about Splay tree. Splay tree, every time you access something, that will immediately become your root. So that next time when you come, you can easily come and start with the root and you will get the node easily. So that's the intention. So in order to make this 4 as your root node, it has these steps. So make 4 the root and 4's right child. That will become the left side of 6. Right? So 4 is becoming the root. 3 will obviously follow. And 6 is going to come down now as a child. And what will happen to 5? 5, you just have to go and tag it to the as a left child of your 6. Okay. So this is kind of a very generic rule that you can have. So whenever you're accessing something, you have to push it as the root. And when you do a zig rotation, it means that the one that you push, its right is going to be the left of your immediate parent node. Okay. So I think these things, maybe you can still take some time and go through it, but I just wanted to cover it quickly to give a high level overview on what is what. Okay, so zag is something which is similar, but the opposite side. Now I do splay of 6. Okay, what do we do? I'm going to make 6 as the root node. That's my intention because it's a splay tree. Whatever you access, that's going to be your root. So I make 6 as the root. 7, obviously it's going to follow. What about 5? Take its left child and make it the right child of 4. Okay, and this is done. So zig is doing something the other side, zag is doing something this side, left rotation and right rotation. Now the combination is zigzag and zag and all the 4. I'll just give a high level overview on zigzag and one more. Okay, so in this case, when I have to splay 3, okay, 3, can I use just a simple zig? It won't work, right? Because it has it is at a very high level. I cannot directly make 3 as the root and do all the other operations. So that's when zig comes. Zig is recursive zig operation. Like you do zig rotation twice. So you make 3, and then you're going to perform a zig rotation on 4. Okay. So I think let me know if it is a little confusing. I'll go maybe slowly. So now just remember this alone. When I make 4, when I use this as the splay, what will happen? Move your 5 as a child of 6. Okay. Just remember this rule and you can easily tag it here. See, when I do this, move 5 as the child of 6 and immediately 3 will be on the top. Okay. So 2 times, doing zig twice. So zig meaning you move it to the root node, perform zig rotation on 3's parent. 3's parent is 4. On 4, if I have to perform, what will I do? I'll push 6 down, make 5 the child of it, and it's done. Okay. So one more thing that we just spoke about, right? A splay tree is something like which will not worry about the balancing factor and all. See the way it has grown. It is like the height is 3 this side and it's still 0. So it's not going to worry about that. So this is how we do zig rotation. Now zag is something I think it is So I think I have to change the name here. This is zigzag. Okay, yeah, this is zigzag. So this is something you do the same way the other side. I'm going to display 7. 7 is going to be your parent. Okay, 7 is going to be your root node. Now you'll push this entire set down. What will happen to 5? 5 will obviously go and tap to your 4 as the child. Okay, and it's just the opposite of this. This is zigzag, this is zigzag. Okay, so that's about AVL rotations. Maybe you can take some time to go through the other 2 combinations, which is again the same. You do one zig and you do another zag, so that will explain it all. Okay, I think we're on time. I'll just quickly take last couple of slides. So yeah, the applications, I think we already spoke about it in the last class also, mainly for sorting algorithms where we have this left subtree, right subtree, one should be greater, other should be lesser. It's easy. It's easier when we use binary search tree because you already know it is already in sorted order. Your entire tree, if you have to put it in an array structure, it will be an ascending order. And if you have to invoke from the last, it will be in the descending order. So it's easy. And now, as I said, in dictionaries, right? So they maintain a lot of things. So Apple, Blame, like everything is maintained. It is all in real time. It is used in dictionaries, all the binary search trees and data caching. Data caching is obviously it's a splay tree where they pull the topmost, like frequently accessed to one, and they use it in data caching. Okay. So any questions? All right. So yeah, I think we had these 2 to cover today, and I think maybe in the interest of time, I have just run through. But yeah, you can still go through and I basically use this Alan Weiss book, which is the book that I follow for data structures. So that is kind of little explanatory, and it has a lot of examples. So you can go through that. Okay.
Excuse me, Pavithra.
Uh-huh.
Can you mention the book author again? I actually joined the session late today for an hour. I couldn't join an hour back. So I
Okay.
missed.
Sure. Yeah, it should be okay. Yeah, because I will probably type it here. And
Okay, thank you.
sure. Yeah. And maybe if you're in our meetup, probably I'll send an email with the details and the recording also.
Okay, yeah, that will be helpful.
Sure, yeah. Cynthia, we have the YouTube recordings, sorry, all the recordings in Women Who Code channel. So you can go to this Women Who
Yeah,
Code.
let me put the link up here for that.
Sure,
The DSA series, I'll put the link.
Sure.
Okay.
Yeah.
Yeah, because I understand this was session 5. So there are some other data structure topics already covered, I guess.
That's right, Lata. Yeah.
Okay.
Sure. Yeah. Thank you, everyone. Thanks for your time.
Yeah, let me just put the link before we close the Zoom session. So it's in the chat. Also, Pavithra, you put the name of the book
Sure.
here, right?
Yeah.
Yeah, just copy these things, guys. So whenever the new DSA session will happen, it will get copied in the same playlist. So this is the link of the playlist where all the previous sessions are there. So this one will come in a few days and we will add it there. Okay, yeah, this is the book. So whoever wanted